title Akshay Babu. Today we are going to talk about Nurbs. NURBS. The full form is Non-Uniform Rational B-Spline. Rational B-splines provide a single precise mathematical form capable of representing the common analytical shapes, which are lines, planes, conic curves, including circles, freeform curves, quadric, and sculptured surfaces used in computer graphics and computer-aided design. Now, a rational B-spline curve is the projection of a non-rational B-spline curve defined in four-dimensional homogeneous coordinate space back into three-dimensional 3D physical space. Specifically, P of t is given as the summation of I is equal to from 1 to n plus 1 bi into bi ni k of t. Here bi's are the 4D homogeneous defining polygon vertices for the non-rational 4D B-spline curve. Nik is the non-rational B-spline basis function given by the equation here 584a and 584b. Ni of 1 is 1 when xi when t belongs to xi when t lies in between xi and xi plus 1 and 0 otherwise. Nik of t is given by t minus xi nik minus 1 t divided by xi plus 1 I plus k minus 1 minus xi plus xi plus k minus t n I plus 1 k minus 1 of t divided by xi I plus 1 I plus k minus xi plus 1. Here the values of xi are the elements of a knot vector satisfying the relation xi less than or equal to xi plus 1. The parameter t varies from t minimum to t maximum along the curve p of t. The convention 0 by 0 is equal to 0 is adopted. Now projecting back into three-dimensional space by dividing through by the homogeneous coordinate yields the rational B-spline curve, which is given by the equation 5122, where the BIs are the 3D defining polygon vertices for the rational B-spline curve, and the Rik of t is given by hi nik of t divided by the summation I is equal to from 1 to n plus 1 hi nik of t are the rational B-spline basis functions. Here hi is greater than or equal to 0 for all the values of t, I for all the values of I. Here we have some properties of the rational B-spline curves. The sum of the rational B-spline basis functions for any parameter value t is 1, that is summation I is equal to 1 to n plus 1 rik of t would be equal to 1. Except for k is equal to 1, each rational B-spline basis function has precisely one maximum. A rational B-spline curve of order k, if the order is k then the degree would be k minus 1, is c k minus 2 continuous everywhere. The maximum order of the rational B-spline curve is equal to the number of defining polygon vertices. A rational B-spline curve exhibits the variation diminishing property. A rational B-spline curve generally follows the shape of the defining polygon. A rational B-spline curve lies within the union of convex hulls formed by k successive defining polygon vertices. And here we have the equation when we take I from 1 to 3, then the rational B-spline function can be written as P of t as the given equation, which in fact is a third order rational Bezier curve. It is convenient to assume h1 is equal to h3 is equal to 1. Then the above equation reduces to the equation number 5130. Now if h2 is equal to 0, a straight line between b1 and b3 results. If h2 tends to infinity, the defining polygon is reproduced. When h2 is equal to 0 and t is equal to 1 by 2, the midpoint of the line b1, b1, b3 labeled m in figure is obtained. Similarly, when h2 tends to infinity, t is equal to half yields the polygon point at b2. For h2 lying between 0 and infinity, the point s corresponds to the point at t half, t is equal to 1 by 2 on the curve p of t along the straight line connecting m and b2. So s is called the shoulder point. The value of h2 determines the type of conic section. So if h2 is equal to 0, then we have a straight line. If h2 lies between 0 and 1, then an elliptic curve segment results. If h2 is equal to 1, then a parabolic curve, and h2 if it is greater than 1, then a hyperbolic curve would result. This is the given figure. So we can clearly see that when h2 is equal to 0, we have a straight line between b1 and b3. If elliptic, then h2 lies between 0 and 1. So if h2 is 0.25, then we will get the elliptic curve. If h2 is equal to 1, then we get a parabolic curve. If h2 is greater than 1, here h2 is given as 3, then we will get a hyperbolic curve. So for t is equal to 1 by 2, p of t is equal to s, will give the following equation. Then writing the given parametric equation of straight line between m and b2, we will get s is equal to 1 minus s capital M plus small s b2, where s is a parameter. Then writing the equating the coefficients, we will get s is equal to h2 by 1 plus h2, and h2 is equal to s by 1 minus s. So s minus 1 by s can be written as m minus s by s minus b2. So equating this, we will get that h2 is equal to E tan theta by 2 divided by f sin theta minus E tan theta by 2. So we can recall that tan theta by 2 can be written as sin theta divided by 1 plus cos theta. So substituting that sin theta by 1 plus cos theta in tan theta by 2, we'll get that h2 is equal to E by f, which is simply cos theta. So suppose the portion of the circle subtended by the arc is twice the angle. The portion of circle subtended by the arc is twice the angle theta. So if an arc is 120 degrees, then theta would be 60 degrees. Then cos 60 degrees is equal to 1 by 2. So h2 will be 1 by 2. Then the radius of the circle is 2 times capital S minus capital M. So if we want to form a circular arc, we have to draw and draw points in equilateral triangle. Like the points should be equidistant to each other and the angle should be 60 degrees. So which means that h2 is equal to 1 by 2. So here we can see that there are 7 points for an equilateral triangle: b1, b2, b3, b4, b5, b6 and b7, and the total angle is 120 degrees. Then the angle would be 60 degrees and h2 is 1 by 2. We can see the code here to draw Nurbs curve. We take the number of control points, then we input the control points and we enter a weight for each control point, and then from the above equations we do it recursively to obtain the graph. We can go to the Nurbs. Here we can enter, suppose we'll we'll recreate this figure 16, figure F569, a 120 degree segments. Then we'll get Suppose we enter control points, we keep the control points as 7, and then we can start in the middle. 5, 1, 2, 3, 4, 5, 6, and 7. So this is almost an equilateral triangle, but not exactly. And we'll give weight for each of the control points. Suppose we keep 1, 0 0.5, 1, 0 0.5, 1, 0 0.5, 1. And the order of the curve as 2, and you keep press enter. Then we'll get the figure as this one. So this is almost a circle. If we would have drawn the equilateral triangle better, then we will get a perfect circle as given in this figure. And suppose we run this code. Suppose we give the control points as 3. Then we try to make an equilateral triangle by pressing the points here, here, and somewhere here. Now we can keep h1 as 1, then h2 would be 0 0.5, and then h3 would be 1 again, and the order of the curve is 2. Then the obtained figure would be like this. This is a circular arc. So when the value of h2 is equal to 0 0.5 for an equilateral triangle, then we would get a circular arc. Now this is about a Nurbs curve. So thank you.